Welcome back. How are you, friends? Hope you are doing good and then enjoying with the lectures. Now we are almost like the final chapter, and then with that I can say the sessions will be over. Okay. Our subject is analog circuits. And chapter 5. Diode applications. Or circuits. We are going to see concept part. Okay, then we'll see the problems. Okay, now before going to the circuits of the diodes, whatever we are going to see, let me classify into clippers and clampers. When I say diode applications, let me classify into clippers and clampers, and clampers. Right? Then first of all, before explaining clippers, let me start with clampers. But whatever it may, whether I start with clippers or clampers, we should know what is PN junction diode. I am not going to explain the device operation which you get from EDC. Let me start with diode approximations and going to exact model. Similarly, I am going to explain when I say PN junction diode. Here I'll explain heavily doped PN junction diode, which is nothing but Zener diode, because we have application of Zener diode which is for regulation. Therefore, let me explain both PN junction diode as well as Zener diode. Then I'll start with clampers, then clippers. Then with that I can say chapter number 5 is also over. Okay. Now write down diode approximations. Diode approximations. PN junction diode approximations. Number 1. PN junction diode approximations. Approximations. Okay, right. Don't write anything, just listen. Okay. Number 1. This is what is category 1. Number 1, first approximation. First approximation, basically this is what is your ideal model. This is what is your ideal model. Okay. What is the symbol of PN junction diode? The symbol of PN junction diode is, this is what is your PN junction diode. This is what is the symbol of PN junction diode. And let us say this is what is the voltage across PN junction diode, and this is what is the current through PN junction diode. Okay. Now people say that number 1, case A, if V is greater than 0 volt, greater than or equal to 0 volt basically, then means if the voltage across PN junction diode is positive, then your diode is on or forward bias. Then how will you represent? If V is greater than 0, then your PN junction diode ideal model, right? This is what is represented as short circuit, because it is on switch. Okay. Now case B, if V is less than 0 volt, basically negative, then your diode is off. What does it mean? The PN junction diode is represented as off circuit. Okay. Now considering this, okay, now if I draw V2I V2I characteristics of your ideal diode, this is what is V, this is what is I. Therefore now tell me, when V is less than 0, when V is less than 0, what is your diode? Diode is off. If the voltage across PN junction diode with respect to P to N is negative, then diode is off, then current is 0. There is no current. Therefore that is what we represent, because I is equal to 0. Now when V is greater than or equal to 0, actually that is the starting point. When V is greater than or equal to 0, that is forward bias, then diode is nothing but on. When I say on, what will be the current? What is the current? Which is what is flowing through the PN junction diode. Normally people represent something like this. What is the meaning of this? When the voltage across the PN junction diode with respect to P to N, remember this is always with respect to P to N, is less than 0 or negative, your diode is open, therefore there is no current which is flowing through the PN junction diode, therefore current is 0 for entire negative voltage of PN junction diode. Now when the voltage is greater than or equal to 0, what is the meaning of this? Impulse. Is it impulse? When the voltage across the PN junction diode is greater than or equal to 0, then current is impulse. Means it will have infinity current. Is it correct? What is the meaning of this? That's what I am asking. If you understand this, right, remaining things are straightforward. If you understand that this is understood by everyone, that's what I am guessing. Because current is 0, it is open, fine, done. But what about this? Okay, let me tell you. The meaning of this y-axis or the curve which is what is lying on y-axis is nothing but, let us say, just I am asking, let us say this is what is circuit 1, okay, this is what is my PN junction diode which is having 10 volt battery, and this is what is 10K, and there is a PN junction diode. Before that, before going to the circuit, that's what I want to explain the meaning of that, right? Now that's what, let us say this is what is your, this is what is 10 volt battery, let us say this is what is your 1 kilo ohm and 1 kilo ohm. Tell me what is the current which is what is flowing through it, and let us say this is what is my switch, this is what is my switch. Tell me what is voltage across the switch. The voltage drop of a short circuit is equal to 0, right? The voltage drop across the short circuit is 0. But tell me what is the current which is flowing through it. The current which is what is flowing through it is nothing but the current which is what is flowing in the loop. That is what is your current. Therefore tell me what is the current which is what is flowing in the loop is nothing but I is equal to 10 divided by 1K plus 1K, 2K, which is basically 5 milliampere. Therefore tell me here, when voltage across a short circuit is 0, but the current which is flowing through the short circuit is nothing but 5 milliampere. Done? Now let me take circuit 2, where now my input is, let us say, 20 volt battery. This is 1K, 1K, and again I am taking the short. This is nothing but a short, and still I am asking what is the current. Tell me what is voltage across short circuit. Voltage across short circuit is 0 only. Voltage drop across a shorted wire is 0. But what is the current? Again the current which is what is flowing through the wire is nothing but the current which is what is dictated by your loop circuit. Therefore tell me what is the current. Your current I is equal to 20 divided by 2K, basically 10 milliampere. Therefore tell me, from case 1, what is voltage across short circuit? 0. What is voltage across short circuit from case 2? 0. What is current through short circuit? 5 milliampere. What is current through short circuit? In case 2, 10 milliampere. For the same voltage, which is what is 0, we are seeing different currents. What does it mean? Actually, the current which is what is flowing through the short, right? The short wire, the shorted wire is dictated by the loop, but it can have a voltage of 0. By having voltage across a short circuit 0, it can support any current that depends on the loop circuit. Similarly, the meaning of this is nothing but the moment when PN junction diode is on, it is a short circuit, the voltage is 0, but it can support any current from 0 to infinity. For the voltage of 0, that current is dictated by the loop where the diode is in the loop. For example, this is what your diode that is on 0, but the current is dictated by the loop parameters, voltage source, resistor, water all there along with the PN junction diode. Therefore, it is not impulse. It has infinity solutions. For the voltage 0, the voltage is 0, but it can pass any current from 0 to infinity. It's not impulse function. It is having infinity solutions. It can be 0, 1 ampere, 2 ampere, 3 ampere, 4 ampere, 5 ampere. Any current it will support with the voltage of 0 because it is a short circuit. Something like your OR switch. I hope everybody understood. This is not impulse function. Okay, it can support any current, but the current is dictated by the circuit loop. Okay, done. Now, second approximation. As the approximation level is increasing, remember, as the approximation level is increasing, we are close to exact model or real PN junction diode VI characteristics. Now, the second one, second approximation, somewhat practical. Because if you take your real PN junction diode, it has some cut-in voltage. That is what is added here. Therefore, if you take that, right, case A, when the voltage is greater than or equal to V gamma, where V gamma is nothing but your cut-in voltage, okay, then only your diode is on. Then what is your PN junction diode? The PN junction diode is represented as a battery of V gamma. It will have a drop. The PN junction diode voltage, PN junction diode will have a drop of V gamma. More than that, if you apply, then only it will be on and having a drop of V gamma. If V is less than V gamma, it is off only, same as your ideal case. Okay. Now what is case B? Case B is nothing but that V is less than V gamma, then your diode is off or reverse bias, anything is fine. Then how will you represent? Your diode is represented as open circuit, absolutely open circuit. Now accounting this, we need to draw the VI characteristics. This is V, this is I. Up to V gamma, tell me, when V is less than V gamma, diode is off, completely open circuit, then completely your current is 0. Your current is 0. But when voltage is greater than or equal to V gamma, it is a battery having a constant voltage V gamma, but it can support any current from 0 to infinity. The battery, the voltage, when you represent with a battery, what does it mean? It has to maintain voltage of V gamma, but it can support any current, right? That is what is the battery. That depends on the load what you have across the battery. Similarly, therefore, the meaning of this is nothing but it will have a voltage of V gamma, but the current can be anything. That depends on the loop where the diode is present. Okay, that is what it is. I hope everyone understood. Now this is somewhat practical, not completely ideal, not completely exact model. Then people incorporated one more level, which is nothing but your current, right? The voltage across PN junction diode is V gamma, that is fine. But most of the time people took the second approximation until unless it is like, if people say explicitly that ideal model, that is very easy to solve the problems. But people say second approximation, then we need to construct the V gamma, then after V gamma it is on only, like battery. But we know that if you take real PN junction diode, if the voltage across PN junction diode can be more than 0.7, 0.7, 0.701, 0.702, then only current will increase. Therefore, the increase in current with respect to increase in voltage above V gamma, that is also incorporated. That is what is third approximation. Okay, I don't have space. You write down That is important, that circuit 1, circuit 2 are example 1, example 2 to explain the meaning of the vertical line for the voltage of 0 or for the voltage of V gamma, the vertical line. Okay, take this, then I'll rub this, I'll write third approximation, then I'll give you finally the exact model. With that PN junction diode approximations are over, then I'll explain for Zener diode. Okay, done. Take it. Case A, we need to include the cut-in voltage V gamma. When V is greater than or equal to V gamma, your diode is on. On means forward bias. Then your PN junction diode, it is not only having a battery, it is also having the resistance, the forward resistance. This is what is your on resistance or forward resistance, and this is what is your V gamma. Okay. Now if you take case B, V less than V gamma, your diode is off. Here also it is taken as off, which is your reverse bias. Then your PN junction diode is nothing but absolutely open circuit. Okay, then how will you draw? This is what, again if you take VA characteristics, V and then I, this is what your V gamma. What is less than V gamma? Less than V gamma, it is absolutely open, therefore absolutely current is 0. And more than or equal to V gamma, not only battery, not only having the voltage, but the voltage, this is what your V. V is nothing but the voltage across this. This is what is your V. This is what is your V. Okay. Therefore, if this V is increasing, means this V is increasing, this V gamma is constant, right? But this V is increasing, then the current through RF also will increase, right? Therefore, what it may be, the current is also increasing linearly. This is what is taken. Okay. Therefore, the slope of the curve is nothing but 1 by RF. The slope of the, because current by voltage, right? Voltage by current is resistance, but current by voltage. Remember, I have represented with what we call RF. But remember, third approximation only, sometimes people take fixed RF. But strictly speaking, if you want to include one more approximation, but still it is called as third approximation, where the RF will be calculated from bias value. Because this is what is your dynamic resistance. The dynamic resistance will be calculated from bias value. What is that? I will explain. Then after that I will give you exact model. Okay, take this. In the problem, if they state that the PN junction diode is having on resistance of 10 ohm, then cut-in voltage 0.7. You can take it as always 10 ohm, 0.7, and then you can solve the problems. But sometimes the on resistance won't be given. Then we need to calculate. But how to calculate the torn resistance? That is what I'll tell you. That is what is your dynamic resistance or internal resistance of your PN junction diode, which is not constant strictly speaking. That is depending on your bias because it is non-linear element. All non-linear elements, the dynamic resistance value or the dynamic portion or the slopes are depending on operating point. If operating point changes, slope changes, means resistance changes or gain changes. All AC parameters will be depending on your operating point. Okay, now the last one, exact model. Right? It is irrespective of anything. That is nothing but if you take a PN junction diode, the voltage across the PN junction is V and current through PN junction is I, the relationship is I is equal to I naught into e to the power of V divided by eta Vt minus 1. This is what is the relation. Right? Then if you ask me, up to V gamma current is not significant. From V gamma, your current is increasing exponentially. But remember, this is a non-linear curve. Okay? And then reverse bias, this is what your I and this is what your V. In reverse bias, your current is not absolutely zero because when V is negative, you can neglect this part. Then your I, whatever you are representing from P to N, if this is 0, 0 minus 1 minus I naught, the current will be flowing from N to P because it is negative. But whatever may be, this equation is valid with respect to this notation. Now when V is negative, your current will be also negative current, but it is almost equal to I naught. It is almost equal to I naught. This is what your reverse saturation current. Okay? But still, if you increase your reverse bias voltage, if you still increase your reverse bias voltage, this is what your reverse bias and this is what is your forward bias. If you increase your reverse bias voltage, means if you apply negative voltage and then you increase, we are expecting the current to be almost zero. Your I naught is almost zero. Okay? Here this current is almost in the order of milliampere and here the current is in the order of microampere. But if I increase, it's almost zero. If I increase my reverse bias voltage, if you take practical PN junction diodes, there is something called breakdown voltage. There is something called breakdown voltage. What do you mean by breakdown voltage? If you increase and then if you reach to breakdown, your current will be infinity. This is what is your avalanche breakdown. But if you take Zener diode, that is Zener breakdown, which is controllable. That's why I am not going into the details why you are getting breakdown and all. That is because of the minority carriers which are accelerated to very high velocity. As the reverse bias voltage is increasing, then they can penetrate through the crystal lattice, then they will break the silicon covalent bond, then they will generate further minority carriers, then they will be accelerated further. It is the kind of chain reaction, therefore your current will be infinity. This is what is your breakdown voltage. This is what is called avalanche breakdown voltage. But remember, once the PN junction diode is entering into breakdown, immediately current will be infinity. We cannot use it further. We have to throw the PN junction diode. That is what is called diode is damaged once. That is the reason why we should not operate your PN junction diode in this order. Let us say the PN junction breakdown voltage in the order of, let us say 20 volt. Actually this is minus 20 volt. When I say VBR 20 volt means with respect to PN junction diode V forward bias voltage, it is negative 20 volts. Okay. Therefore when this is what is 20 volt in the order of 20 volt, then you know it will be entering into breakdown. Therefore don't apply more negative voltage to PN junction diode practically. Now I can correlate third approximation to exact model little bit. If you see here, if you don't bother about the breakdown portion, this is what is your breakdown portion, avalanche breakdown portion, but whatever it may be, except this, it is almost matching to your third approximation. If you want to match to the point to exact model, then wherever you are defining your operating point, then the slope of that can be represented there. For example, if I operate here, the slope that can be extended and that can be represented. If you define your operating point here, you take the dynamic range and then slope, then draw a line, that line you can represent. Therefore, actually that RF can be changed. The RF is different with respect to your operating point. But how will you get it? Therefore, RF is nothing but your dynamic resistance. Your RF is defined as dynamic resistance. This is your dynamic resistance. Because this is not, is this linear or non-linear? Non-linear. For non-linear circuits, we need to define the resistance as dynamic way. Therefore, this is your dynamic resistance. How will you define? This is nothing but your dV by di. Delta V by delta I. Do you know V? No, I know I. Therefore, what I do? 1 divided by di by dV. That also you can do. You call this as equation 1. You call this as star. Right? Now, star implies, what is di by dV? Di by dV is nothing but I naught is constant into, because with respect to voltage, not with respect to temperature. Okay, we are differentiating with respect to voltage. E to the power of V by eta Vt into 1 by eta Vt. Therefore, can I say this is nothing but I naught into e to the power of V by eta Vt divided by eta Vt. But what is I naught into e to the power of V by eta Vt? I naught into e to the power of V by eta Vt is nothing minus I naught. That I naught, if you take to right hand side, left hand side, this is nothing but your I plus I naught divided by eta Vt. This is exact value, or approximately you can say I, because I is forward bias current, I naught is reverse bias current. Your I is forward bias current here I naught is nothing but your reverse bias current. That you can ignore. Then I divided by eta Vt. Therefore, if you take 1 implies, what is your dynamic resistance in forward bias, during forward bias? That's why F is indicating only that is true in forward bias. Okay, whatever you are doing here, that is true only in forward bias. Therefore, RF is nothing but eta Vt divided by I. If eta is equal to 1, it is simply eta Vt divided by I. What is Vt? Where Vt is nothing but Kt by Q, which is 26 millivolt at room temperature, or 25.9, anything is fine. And I is nothing but your forward bias current or your bias current. Therefore, your dynamic resistance is depending on your DC current, which is nothing but your bias current. Wherever you are operating your PN junction diode, there if you take the tangent is nothing but the slope of that curve at a particular point. If you change different operating points, then the tangent slope will be different. That slope only we are representing in the third approximation. Therefore, we can correlate almost third approximation to the exact model, except the I naught, which can be neglected, and the breakdown is not accounted. That is what is your third approximation. Now you can take it. Then after that, I'll explain Zener diode. Remember, in PN junction diode, we don't want to operate PN junction diode in breakdown. Once you operate, or once the PN junction diode is entering into breakdown, we cannot use it further. But if you consider Zener diode, we always want to operate in breakdown only, because Zener breakdown is controllable phenomena. Even though it is entering into breakdown, we can retrieve it back and then enter into forward bias also. But here, once it is entering into breakdown, we cannot use it. Once it is entering into breakdown, it's like current will be infinity, then we cannot use it further. But Zener diode, it's not like that. Okay? That's why we will use Zener diode as a battery under breakdown. If you want on switch, you can use Zener diode or normal PN junction diode. Only the Zener diode application is breakdown. Therefore, let me explain only breakdown. Normal form. Category 2. Okay. Now, if you take your Zener diode, what is the symbol of Zener diode? The symbol of Zener diode is, this is what your Zener diode, it's like Z. Okay. And if the voltage across the Zener diode is V and current through Zener diode is I, again it is same as I is equal to same I naught into e to the power of V divided by eta Vt minus 1. Remember, it is exactly same as your normal PN junction diode. If you take approximation, diode approximation 1, 2, 3, you can apply for your Zener diode also. But in the case of PN junction diode, we don't want to operate in breakdown, avalanche breakdown. But in the case of Zener diode, we can operate in breakdown. That is the speciality of your Zener diode. Except that, whatever reverse bias, forward bias you have for Zener diode, exactly same as your PN junction diode. When I say Zener diode is in forward bias, if you take approximation 1, short it. When I say Zener diode is in reverse bias but not in breakdown, then open it. It is same as your PN junction diode. But Zener diode can be in breakdown. Then what is that? That is what we need. Because I already explained what is forward bias, what is reverse bias under approximation 1, approximation 2, approximation 3. The same thing whatever we had seen in the case of PN junction diode, they are applicable to Zener diode also. But only the specialty of Zener diode is breakdown. Under breakdown, what is that and how it is equivalently represented? That is what I am going to show. Okay, that maybe I can say if you take exact model, right, of this Zener diode also, it will be like this up to V gamma. Current is not significant. After that, it is increasing exponentially. This is I and this is V, and now this is almost 0. It is almost 0. This is what people call it as your I naught or Zener D current, but this is what is your breakdown voltage. People call it as VZ. That is what your breakdown voltage. We try to operate, then it is controllable phenomena. This is what is your controllable phenomena. But we should not cross something. That is what people call, right? Therefore, this is what. Now, if you ask me with respect to the category, right? This is what your forward bias. Current will be in the order of milliampere. And now your I naught, this will be in the order of nanoampere or what it may be, the reverse saturation current, whatever you have here, in the order of microampere you can take. This is what your reverse bias. But now this is what is your avalanche breakdown, sorry, Zener breakdown. This is what is your Zener breakdown. We try to operate, right? Therefore, it is used for regulators. That is what. Therefore, I need not explain, right? Forward bias. If you take ideal model, short. V gamma, parallel. V gamma with R, exact model. Reverse bias, almost 0. But only the specialty thing is Zener breakdown. Okay? Therefore, if you consider only Zener breakdown, when you consider your Zener diode, right, in breakdown, under breakdown, again, number 1, ideal model. When you take ideal, that is what people represent only in breakdown. Up to V gamma, it's almost 0, you can say. The Zener D current is 0. But here, people represent like this. But practically, we don't have like this. But this is ideal model. I'll explain what is the meaning of this. This is what is your V Zener. And people call this as your IZ minimum, the minimum Zener current under breakdown. Only under breakdown. Whatever I'm explaining is under breakdown. And we should not cross a maximum current, because even though I say that your current can be anything, no. If you cross some current, more power dissipation, it will be burnt. Therefore, it is also defined with maximum current. That is what is your IZ max. Now, why it is acting as a regulator? See, what is a regulator? Irrespective of the current, whatever it is flowing through something, if its voltage or the voltage generation from it is constant, that is nothing but what voltage source or voltage regulator. Similarly, if you see here, if you keep your Zener diode under breakdown, the voltage across the Zener diode is almost VZ, but it can support any current from minimum to maximum. If you observe clearly, the change in the Zener voltage, is almost 0, without any change in the Zener voltage, but it can support any current from minimum to maximum, then it is not battery. That is battery, right? Battery with the voltage VZ. Battery with the voltage VZ. But remember, this is true only when it is in breakdown. Therefore, if this is what is the case, right, this is what is your ideal model, then your Zener diode under breakdown is represented as a battery of voltage VZ. People represent Zener breakdown as VZ here. When I say Zener diode and then 6 volt, meaning of that is the breakdown voltage is 6 volt. Okay, if you cross 6 volt, then only it will enter into breakdown. Once it is entering into breakdown, then only it will act as a battery, which is what is VZ. Okay, now this is what your ideal model. But if you take practical model, this is actual real model, which is nothing but this only, which I wrote there. For this is what your practical model for breakdown. Therefore, if I take that part, it is having the Zener minimum, but it will have some variation. Therefore, this is what your VZ and then corresponding IZ minimum, and everything is supported by IZ maximum. But remember, there is some variation in VZ. There is some variation in the VZ. Therefore, for a small change in VZ, it will support the current from minimum to maximum. If you neglect the small change in VZ, then it can support the current from minimum to maximum. Therefore, it is nothing but a battery, right? But it is not ideal battery, it is a practical battery. If you take ideal battery, the change in VZ is nothing, but it can support from the minimum to maximum. That is nothing but a battery. Whatever may be the current you draw from the battery, depending upon the circuit or load what you connected, then the current is defined. But it will support always VZ. That's why it is equivalently represented as a battery. Therefore, that battery will be given to load, where load always sees the Zener voltage, which is nothing but your voltage regulation. Okay, that's fine. Now, here, how will you represent? This is what your practical Zener diode. This is what is represented equivalently as it is having Zener resistance. People represent RZ and then VZ. If you ask me what is RZ, RZ is nothing but Zener resistance is nothing but delta VZ divided by IZ maximum minus IZ minimum. IZ maximum minus IZ minimum. Ideally, the delta VZ should be 0. Then only I can say it is almost battery. But practically it is not a battery, it is having some on resistance. Okay. Remember, these two are valid only when the Zener diode is in breakdown. What do you mean by breakdown? The reverse bias voltage should be greater than or equal to the Zener breakdown voltage. Then only it will enter into breakdown. Then only we can use like ideal battery or practical battery. Okay. Write it. If not in breakdown, same as your PN junction diode. Okay. Forward bias, reverse bias. But breakdown, these two are the cases which we did not see in the case of PN junction diode. With this, I can say the concept or the theory related to the PN junction diode and Zener diode is done. Maybe we can use this theory to solve the problems, or we can see the circuits. Therefore, we will understand the applications part. Okay. From next class onwards, we will solve the classroom problems, classroom workbook problems. Then, after solving them, we will go to student workbook problems. Okay. With that, I can say chapter 5 is over. Here, my way is by solving the problems, the theory will be covered as well as how to solve the problems also will be covered. Okay. Okay. Please continue. I will stop this session. Thank you.